Good morning, good afternoon, good evening. Thanks everyone for joining us here for the DAS workshop, day 3. I'm going to go ahead and let Nate Lindsey take over.
Okay, thanks for everyone for joining. We're going to start off this morning with lightning talks, but as we get started here, I think we looked at some of the numbers from day 1 and day 2, and we just wanted to summarize this fact that we have over 200 attendees on both day 1 and day 2, many of which were able to join for more than an hour from over 28 countries, and so we're kind of excited to be able to kind of open up this this workshop to so many of you. So with that, we're going to get started with the lightning talks this morning. So these are individuals that are in the workshop, and you should be able to see my screen here. I'm just going to copy. I think the order here is listed and should be in the chat also, or one of my co-organizers can copy it in there. So we're going to get started with Patrick, and Eileen is going to be timing everyone. We're going to auto advance at 2 minutes, so keep these quite brief, but hopefully it gives you kind of a whirlwind tour of many different DAS topics that are here. So please, when you see your slide, just unmute yourself and begin talking, and just kind of keep to your 2 slides or 1 to 3 slides in 2 minutes. So is Patrick here, hopefully?
Yes. Can you hear me?
Good, yes. Okay, so let's
awesome.
With Patrick.
I don't, is this slide up? I don't see it right now. Let me check. Yep, all right, cool. So yeah, good morning, good afternoon, and good evening. From my side, I'm Patrick Paitz, and I've been working on various DAS experiments throughout the last 3 years here at ETH Zurich in Switzerland. And what you can see here on the slide is a small overview of one of our most recent experiments and publications that discusses the potentials of DAS in a cryoseismological context. And in our initial experiment, we had a fiber surface installation of in a triangle shape of about 300 meters side length. You can see that in the center on the top. And the cable was trenched in snow on the glacier where you see the arrow on the top left. And we recorded less than a week of data during winter time, basically. And with that data, we were able to precisely locate glacier stick slip ice quakes, pick seismic phases, and estimate glacier thicknesses and material properties, just based on the DAS recordings, passive recordings. And because the first experiment provided some quite useful insights, especially on the practical side, that it's easy to transport and deploy fiber over large distances on the glacier, with great temporal and spatial resolution on the data acquisition side, we went back this summer with a larger installation and deployed 12 kilometers of fiber. And yeah, therefore we needed some more advanced deployment methods, as you can see on the bottom left. I think this sled is twice my age. And we used that to deploy the fiber over the entire glacier, basically from top to bottom, and repeated the recordings during summer throughout the whole month. And the goal there was really to sample the entire glacier and explore all possibilities of these longer arrays for all sorts of cryoseismological things. And yeah,
we're out of time and have to move on to the next speaker.
Yes. That's
we'll be strict.
Next slide then. Oh, sorry, one more. Hello everyone. We did a DAS experiment on Mount Meager, an active volcano in Canada with the highest geothermal potential, but also prone to massive landslides. That's why we installed a 3-kilometer long cable there, which goes around in loops, partly on the glacier and partly on the ridge. And this gave us 1 month of measurements at the end of summer last year. Next slide. One thing We found in dataset were thousands of high frequency events in the band between 5 and 45 Hertz. The figure on the left shows the distribution over time compared to the broadband seismometer and the geophone co-located with the cable. This confirms the overall trends in the data and the events. The other figure shows that the event seems to follow a power scaling law, which means that we're likely looking at events with natural origins. And some of these events are highly similar, with waveform correlation coefficients going up to 1. So we wanted to learn more about these events, and that's why we applied beamforming to DAS data. Next slide. Each dot in the figure on the right represents the beamforming results of one event. And we can see some very distinct clusters of the events, and that the predominant direction is still in the direction of the main peaks of the volcano. So these events could be volcanic in origin, but they can also be earthquakes, rock falls, ice quakes, or fluid movement. So this is what we've been looking at. And so if you have any questions, feel free to contact me later. Thank you.
Thanks, Sarah. So Matt.
Hi, I'm Matt Becker. I'm a hydrologist. So this is a kind of a hydrology poroelastic example. And the motivation for this is I work in fractured rock, and when water flows through fractured rock, it kind of goes through plumbing rather than, you know, open up like it would in an alluvium. So we always have to find out exactly where the water is going, and it's very hard to measure distributed pressure. So we are instead measuring the strain resulting from the water pressure opening and closing fractures. So you can see an experiment that we did. There's a well field on the bottom left here. And what we did is we injected and pumped out of one well, and then we observed in a number of wells, but I'm going to show you the one that's labeled 10 and the one that's labeled 9. And those responses are shown on the right. So these are profiles of a DAS cable laid down into or hung into a borehole. Then we used a flexible liner to sort of push that cable up against the wall. So what you're seeing is the amplitude response of all the channels in response to multiple periods. So the longer the period of injection and pumping, the greater the strain we saw in the fracture, which would be expected. So what I want to point out is sort of the distributed nature of the strain, because we haven't talked too much about that. You can see that there are kind of lumps in this, and that's where the fracture is opening and closing, and we're picking that up with the cable. The little figure in the middle shows what happens when you strain one single point in a cable. And so Nate talked about gauge length, and I wanted to put this in here to illustrate that you never really, though we're measuring every 25 centimeters, you can't see any differentiate strains within 10 meters. So it's sort of a moving window. So that little displacement location is a point, but you see the strain in the cable.
Okay, great. Thanks, Matt. Next.
Okay, so thank you, Nick. So this is Ben. I'm a postdoc at Colorado School of Mines. So basically, I started working on DAS since last year, all because of this Commons project I'm showing to you right now. So basically, on the top left is the map of the field, which is right outside of the department of our geophysics, the building of our geophysics department. And this field is about like 27 meter by 30 meter, and basically, you can see a lot of objects is buried into it for students to explore the geophysics exploration experiments. And also the blue grid is showing the trenches dig into the ground for 1 meter. You can see in the middle of the picture in the middle. And basically we also place the DAS fiber in this grid, and you can see on the bottom left, this fiber kind of wrap around in this grid in this kind of shape. So the main character about this array is that we have crossing fibers. It's like two linear segments crossing each other without the turning corner and this kind of thing. So basically we can explore the directionality property of the DAS array. So we have a paper out this summer about using this array to do passive surface wave experiment, dispersion inversion, using both the earthquake surface wave and also ambient noise cross correlation. So I encourage you to take a look at this paper and get more into the details about directionality, how it's used in surface waves. Next slide, please. Next slide. Next slide, please.
The final one for this one?
Just the next one.
Yeah, that's the next person. So
this one. No, the upper one. Well, it's okay. It's just some fun signals I want to show for what we recorded using the same array for educational and research purpose. Students are interested in this data. They ask for this data for their course projects. So this is a great array for both research and education.
Thanks, Ben.
Thanks, Ben.
Thank you.
Okay, Sam.
All right, hello everyone. I'm Sam Hone at Penn State, and I'm working with the Penn State 4C array. You can see the map here, which is a dark telecommunications fiber with a Silixa IDOS interrogator that runs through State College, PA, right by the campus. It's about 5,000 meters long approximately, and it's been continuously monitoring strain rates since April 2019. We've extracted a number of signals, including earthquakes and various types of urban noise, but what I really focus on is thunderquakes, which is ground motion which is caused by the interaction between the acoustic wave of thunder and the solid earth. This tends to produce largely air-coupled Rayleigh waves. So next slide, please. Sorry, next slide, please. Okay, yeah. So this is what the signal often looks like in the data. You can see they're very common in the data, and they easily detectable because they tend to be quite broadband. You can see around 20 to 150 hertz, and they span the entire array. Some potential uses for these could be as a seismic source similar to an earthquake in areas that lack earthquakes, and they also offer some perspective on storm tracking and the coupling between the atmosphere and the solid earth. Next slide, please. Okay, so for my project, I've identified a number of thunderstorms in the data over the last year for a total of about 123. And I've used manual first picking and then a grid search technique to sort of constrain the propagation velocity and some source locations for the thunderstorm signal. And right now I'm looking at implementing some form of surface wave tomography to get a velocity model of the Penn State area, which I will then validate with active source surveys. And that's everything.
Great. Thanks, Sam.
Mm-hmm.
Junzhu.
Hello, this is Junzhu from Penn State. So since DAS is usually with a huge data set, I'm going to share the idea of an open source GUI to visualize data straightforwardly. And a user-friendly of GUI could also benefit a broader group of people who are interested in DAS but don't want to spend time on codings. This is just a prototype I write for Penn State DAS array. It can read TDM's format or pre-saved MATLAB or NumPy files. In this example, by typing start and end time, I load 10-minute data for plot, choose sampling rate and channels, click the plot, and will pop out the main window on the right. And you can plot a small section of data by specify the parameters. And the basic data processing, including dmin, dtrain, bandpass, is also available. And next slide, please. Next slide. Yeah, and for example, I can choose plot the 1 minute data and push the buttons on the top, like back and next. I can go through every minute to check the signals I'm interested in, and also just maybe just check the data qualities. And on the right, I can also do the wiggle plot to look for the specific traces. And the more functions will be added in the future. And if you are interested in this software, or if you want to like develop this together, just feel free to email me. And that's it.
Thanks. Great open source tool. Luz?
Hi everyone, my name is Luz Garcia. I come from the University of Granada, in Spain. First, thank you to the organizers for this fabulous workshop. My research group works in signal processing, and we have a long history in performing automatic detection, classification, and picking of seismic events, lately using deep learning approaches. We are very new in working with that technology. We haven't started yet, but we are in the process of acquiring a distributed acoustic sensor from a company from Spain called Aragon Photonics, which uses a technology called chirp pulse phase sensitive OTDR. We plan to use it in seismic campaigns that in which we work normally, and also we would like to use it for intelligent traffic management in cities. We want to sensorize traffic of vehicles and pedestrians. Next slide, please. Next slide. Next, thank you. So we would like to we plan to first install a proof of concept in the building of our engineering school, the campus of the university. You can see there the yellow line that surrounds our building where we plan to install optical fiber, and it happens that we have a classical seismic accelerometer 260 meters next to our building. So we plan to use these two sensors to compare them. Next slide, please. Next. Next slide, please. Okay, so the idea is to compare the sensoring of point sensors for pedestrians and vehicles with those of the information acquired from the DAS sensor. So first thing we need to do is be able to extract some information. So that's all I wanted to tell you. Thank you very much.
Yeah, I apologize for the delay. You know, I am clicking when you say next slide though. So thanks for that instruction.
That's okay. That's okay. Thank you very much, Nate.
Rob.
Hi, I'm Rob Abbott, Sandia National Labs, and I'm going to talk about some recordings of explosions out in the Nevada desert, large chemical explosions up to 50,000 kilograms. The geometry in the center figure there is we have a central borehole in which you put these explosions. We have fiber downhole in two different azimuths at 80 meters, connected by a cord of that 80-meter circle, plus in the green, a 2-kilometer long straight section of cable all the way back, trenched in on the surface to the recording site. Next slide, please. So this is the service recording. On the x-axis, we have from 20 meters to 1 kilometer, and the y-axis is about 3/4 of a second. As you can see, we have in the green arrow, the P wave coming in. What I want to focus on is this blue arrow, which has a very high frequency signal about 100 milliseconds afterwards that we were interpreting as SPAL. SPAL usually happens when you have an upgoing P wave hit the surface, goes back down, and the two tensile portions of the wave meet, overcome the tensile strength of the unit, and then it flies up. What is odd is this SPAL continues out to 500 meters and is completely 100% 100 milliseconds the entire time of flight, which means the Earth went up as a piston of 1 kilometer diameter and fell down, which is physically fairly impossible. Next slide, please. So on the right here is the DAG 2 explosion. It's the same as previously. What we see is we have, this is the deep, shallow, the surface section, shallow, deep again. We see here we have this 100 millisecond quiescent period, this slap down signal here, and you can see the large signal. But these arrows here represent this, this 1 strain meter here, which shows that we, instead of just a normal SPAL, we have a continuously up-moving dislocation cavity type SPAL that travels up the cable with, it's a rarely if ever seen before seismic phase.
Very cool. And perfectly on time.
Hello, everyone. My name is Evgeniia Matuganova. I'm a PhD student at GFZ-Potsdam. And I would like to talk shortly about coupling noise problems you're using during DSP wireline acquisition. And I will demonstrate an example dataset acquired in a 1.3 kilometers deep geothermal well at the Gröschenberg site in northeast Germany. Next slide, please. And there are animations there, so there is actually this. Could we go to the presentation mode if it's possible? Because we're
Yeah.
Okay, yeah, everyone will skip it.
Yeah,
Down, yeah, below this plot on the left, there is raw vertically stacked correlated fiber-side data. And if you could see it, you'll notice that there will be regularly occurring narrow bands noise patterns. And then if you would just have a closer look on the certain depth region showed here from 611 to 700 approximately, and we will take an envelope attribute calculated from the selected data, we will see this plot showed in B, and it resembles the theoretical cable displacement for corresponding frequency modes inside the borehole showed in figure A. So we think that the sensor cable acts like the vibrating string within the affected intervals, the resonance occurring at fundamental frequency and higher overtones. And then if you correlate these types of the signals with standard sweep signal, then we will get the plot show on the right, this exact pattern. Next slide, please. And we suggested to use matching pursuit decomposition of Gabor atoms for noise characterization suppressions. And on the plot A, we will see the input signal. On the panel A, that we were trying to represent as a weighted sum of Gabor functions. And by analyzing the statistics of the noise, we're able to identify the noise parts of the signal representing the lapping of the cable on panel B. And then, yeah, on panel C.
It looks really good. Thank you. Weichang.
Hello, everyone. My name is Weichang. I'm from Aramco's Houston Research Center. So this quick talk will be focused on the effect of gauge lengths and the fiber lengths on the signal-noise ratio in the VSP application. It's actually part of this year's SEG paper that I had worked with Harold, Max, and Andre. Next slide, please. So the data set we're obtaining in our in-house testing well, where we run 5 different fiber lenses, 4 different gauge lenses, and run 8 VSP shots, each consisting of 4 records because of 2 downgoing and 2 upgoing legs. And this gives us total 640 shot records. Next slide, please. And yeah, so on the slides, the top half of the slide shows four VSP shots with different gauge lengths. And you can see from left to right how the noise level increases as the gauge length reduces. And the bottom half of the slide shows a step taken to calculate the signal-noise ratio. So basically after first break picking and flattening, the rest of the steps are straightforward to follow. Next slide, please. So here are the main results and take-home message. So first, the signal-noise ratio will increase with increasing gauge length as expected, about give you 8 decibel from 2 meters to 4 meters, but the gain will decrease towards larger gauge lengths before saturates, which is consistent with a paper published by Dean and etc. in 2017. The second is the signal ratio will increase significantly as the channel fiber length decreases, give about 6 to 9 decibel difference. So near channels have better quality than far channels. The long gauge lengths can average out noises, but probably not that helpful in addressing signal degradation. Thank you.
Thanks. So moving right down along to Carlos.
Oh, hi everyone. This project aims at improving the frequency response of DAS below 0.01 Hertz. This is mainly to allow the detection of tsunami waves. This project is the collaboration between a geophysics team at GeoSur in France and the optoelectronics group here at the University of Alcala here in Spain, which itself has a collaborative agreement with DAS equipment manufacturers such as Omnisense and Aragon Photonics. Next slide, please. So instead of using a single frequency pulse as in a conventional implementation of DAS, we apply a sharp pulse where the instantaneous frequency changes with time. The principle of operation of a short pulse DAS is very much the same. It's you're still monitoring Rayleigh backscattering. However, this approach does afford a few key advantages as it yields a more direct detection of the perturbations along the fiber. And it also makes for a more efficient implementation since the optical design requirements are not as strenuous as with using a narrow bandwidth pulses. all of this also while improving strain density sensitivity. I mean, so in the graph below, the graph shows the noise floor. Sorry for the noise. For the high frequencies, we're already approaching the theoretical limit. However, there's plenty of room for improvement in the low end frequencies, so 2 hertz and below. So we're mainly applying strategies to fend off 1/f noise in the measurements. On the picture there, you also see a DAS interrogator wide open with all its innards all splayed all over an optical test bench that we're currently, it's a work in progress. Next slide. And just to show that these are some of the site locations for our testing and characterization, we're mainly making use of existing optical fiber links, telecoms, and piggybacking off of existing infrastructure. That's it.
Great, thanks. Bruce.
Yeah, hi, Bruce Howe, University of Hawaii, Joint Task Force for Smart Cables. Looks like some of the title disappeared here. So there are about 1.5 million kilometers of cable connecting the world together, submarine cable. And the goal of the Smart Cables Task Force is to integrate sensors into the repeaters of these cables in order to measure tsunamis, earthquakes, climate, ocean, sea level, and more as a first order addition to the Earth and Ocean observing system. The basic idea is, again, to put actual sensors into repeaters shown here on the left, and then here on the right here, the little picture of a repeater. Initially bottom pressure, temperature, and seismic acceleration. Later on, after we get this working, one can consider fiber sensing. Next slide. So the basic idea is to share the infrastructure to reduce cost for the science component. And want to emphasize that this particular project, Smart Cables, is for in situ sensors in the repeaters to form mini observatories. Basically, it's a seafloor power and communication interface in general. DAS complements SMART, absolutely complements SMART. And presently DAS is only possible from shore, maybe ultimately more. Ella Link is a system going in, and it will have the first dedicated fiber for DAS sensing. I list some positive aspects here, and the next slides basically just show examples of projects that are underway or starting, and then the last slide references. Thank you.
Thanks, Bruce. So moving right along to Dante.
Hi. So I am Dante Fratta with the University of Wisconsin-Madison, and most of the topics that we have presented today, they were related to geology and geophysics application, but we can still use DAS for other applications, including monitoring the infrastructure. Like high density arrays will allow us to be able to monitor long pieces of infrastructures, such as roads, railways, and pipelines, and also start using dark fibers that is crisscrossing the city. We can start monitoring the responses in different directions. So what I wanted to present today is some of the results that we have been doing along in Garner Valley. That is a site of University of California, Santa Barbara. And we put an array of about 700 meters array that was trenched next to Highway 74. And we were monitoring this with an Silixa IDAS interrogator. So next slide, please. Okay. So what we typically have done and we have seen is that monitoring the speed of vehicles. And we can monitor the amplitude and the speed and be able to evaluate the density of traffic. But if we go into much more details, we can start evaluating the different type of sources that we can have as a vehicle travels through a roadway. So as a vehicle hits, for example, the bump at the end of the bridge in the approach to a bridge, or we hit the transparent cracks or even potholes, we can start monitoring the quality of the roadway. And this is quite important for the transportation agencies. So we were able to monitor and evaluate each one of the diffractors that we have, the sources that we have created by this imperfection on the roadway. And we went back and using Google Earth Maps, we can able to monitor the presence of different transverse cracks throughout the site. So thank you so much.
Great, thank you, Dante. Doug Miller.
Hi, I maintain a very old-fashioned page at MIT with links to papers and presentations I've done over the years. I think it'll come up if you Google Doug Miller MIT, and I commend it to you for more information. I was an advisor for Silixa from 2011 to 2018, so I've seen quite a bit of DAS data and participated in quite a few DAS workshops, and I was significantly involved in the initial analysis of the Poro-Tomo surveys at Brady Hot Springs. For the 2018 Stanford Geothermal Workshop, I prepared a presentation that gives a fairly detailed overview of 4 distributed optical data sets that were recorded at Brady's. Next slide, please. That's temperature twice and vibration twice. This slide shows part of figure 10 from my Stanford report. Now, if you sum all the values for each DAS channel in each file, you get slow fiber strain that can be directly compared with temperature change per minute as recorded by the distributed temperature survey. The match shown here between slow strain and temperature variation at the Brady's vertical well is remarkable. And it's a bit puzzling when you consider that the thermal scaling coefficient that makes this match is about 1/100th of what you would predict if you considered only glass and steel. Evidently, the goo in this loose tube cable has a significantly smaller thermal expansion coefficient than either of those other 2 things. The events here are part of repeating a heat exchange process that persisted throughout the survey period and was still evident when Chris Kratt and Scott Tyler from UNL repeated the temperature survey in 2018. Next slide. I've included my conclusion slide from the Stanford presentation, but I won't attempt to read it. I invite correspondence for anyone who has detailed questions or interpretive observations regarding Brady, or from any of these other very fascinating surveys that have been described today. Thanks very much.
Thanks, Doug. So our next presentation is a pre-recorded presentation by Rob Mellers. So I will just play it here.
Good morning. I'd like to describe some of our efforts in building a homebrew interrogator. This was designed. We decided to build a dual pulse system that sends out 2 separate pulses with the space between them corresponds to the gauge length, and then the reflected pulses beat together to give a beat frequency, which gives you an idea of the phase. In summary, a simplified schematic is in the middle. You then have a laser, it creates a pulse. This pulse is then carved into 2 separate pulses with specific frequency by an acoustic optical modulator. This is then boosted, sent out to the fiber. The reflections from the Rayleigh scattering comes back and are recorded by a photodetector. This measures optical intensity as a function of time. And that's the raw data. And you can see at the bottom right, an FFT, a power spectra of the return signal. All in all, it costs about 70K in parts. It's all commercial, controlled lab view, the actual schematic. For data processing, we actually do it all in post-processing. This limits the collection time. The raw data is optical intensity as a function of time. This is a big matrix, number of pulses by the recorded pulse length. We take that data, filter it, you apply a Hilbert operator and demodulation to get I and Q components, filter again, convert the I and Q to phase using arctan, you then unwrap the phase. This post-processing is all written in Python. Examples of the output are on the right. Time domain, upper right. Red was the signal going in for 40 Hertz. Blue is what we recorded. And on the lower right is a FFT of the results. So all in all, it's not as sensitive as a commercial operator, but it is possible, and we have more documentation if anybody's interested.
Excellent.
Thanks very much to all of our lightning talk speakers. Now we're going to go into up until 12:50, so about 14 minutes, we're going to be in breakout discussion rooms. So when you're in your rooms, if it's new people to you, start off with some introductions. Say your name and affiliation, and maybe one thing that you've learned this week about DAS. Then we want you to discuss some more about those Brady Hot Springs and Forge notebooks. All those discussion questions, I think many of you got a little bit of a taste for it last time, and a lot of you probably tried more in-depth stuff after the workshop. And so if you can go to this Google Doc, which I'll copy the link into the chat and also as a message to the rooms, go to that Google Doc and start filling out some discussions of what you saw and what you observed in the Forge and the Brady Hot Springs notebooks related to those discussion questions. Also, if you did any analysis beyond what was in the notebooks, we'd love to see that. Feel free to copy paste like figures or code snippets, things like that into that discussion document. We would love to see what people did, and the Drive discussion document is really just there for people to share with the broader workshop as a whole. But we want you to also be able to, just discuss within your rooms too. So we'll go into breakout rooms now. We'll try to sort of evenly distribute the workshop guides and organizers.